So I've already written on the board what I wrote, the last things I wrote last time, namely the definition of quantifier elimination. A theory has quantifier elimination, or short QE, if every L formula is equivalent modulo the theory to a quantifier-free formula in the same number of free variables. And I stated, though I did not prove the criterion for quantifier elimination, you remember what we discussed is it suffices to check that every simple existential formula, namely one with a single existential quantifier and the rest quantifier-free, is equivalent to a quantifier-free formula, because then somehow you can use induction to get it for all formulae. And so the quantifier elimination criterion which we'll use today is it's equivalent that the theory T has QE, and for any two models of T with a common substructure A, which I've just written here like A is a substructure of M and N, and for all simple existential formulas phi, say in n free variables, and for all A1 and up to AN in the universe of the common substructure, if phi holds on A in M, then phi holds on A in M in N. And if the language has no constant, then in this one theorem, A is allowed to be the empty structure. Otherwise, structures are always non-empty. Yeah?
So is this just one direction of the conditional? Is the other, do we get the other direction for free by just interchanging the roles of M and N in the...
Yes.
Okay.
Or by, yes.
Okay.
Yes, because it's for any two models. So. Okay, so I promised to apply this to show that the theory of algebraically closed fields has quantifier elimination. I want to start with a toy example to warm us up. So I look at T infinity. This is a theory in the empty language, so there's only the logical symbols. And T infinity says I'm an infinite set. So for every n, we have an axiom of the form there are x1 up to xn, and here you can see n many existential quantifiers, such that xi and xj are different for I not equal to j, and I and j run from 1 to n. And this sentence for every natural number n. Maybe every positive natural number n, whatever. Okay, so now I want to prove theorem T infinity is complete. Complete, you remember, means it's a consistent theory such that it entails every sentence or its negation. So it's complete and has QE. Okay, and it's obviously consistent. Any infinite set is a model of the theory of infinite sets. So and then by what we did last time, if it's consistent, a theory without constants, in a language without constant symbols, which has QE, is either inconsistent or complete. That's one of the things I did at the end of the last lecture. So completeness follows from QE. So SL contains no constant symbols. So that I commented on this last time. So let M and N be infinite sets, and A a common substructure, which just means a common subset. Because there is no further structure. Okay, what do I need to take? I need to take A1 up to AN, some elements in the universe of the common subset. So in I, and phi x1 up to xn, a simple existential formula. Okay, so just to remind you, this means phi of x bar is equal to there is a y, rho of x bar y, and y is a single variable, and rho is quantifier free, so no quantifiers occur. And now, okay, what am I given? I need to assume phi holds on my tuple a bar in M. And now I want to show that phi also holds on my tuple a bar in N. So in order to do this, so maybe we need to find C in N such that N says rho of a bar, comma C holds. Right? Because that exactly means N models there is a y such that rho of a bar y holds. Okay. So, but in my language, right, I have no symbols. I mean, I have no symbols but the logical symbols, so I cannot say very much. Okay, so what can my formula rho say? Maybe it says C is equal to one of the AIs. Right, so if, first of all, let me also give a name to the corresponding y in M, say M models rho of a bar, comma b, or an appropriately chosen b. If b is equal to one of the AIs, I can just set C to be the same AI. Right? Because what can my formula say? It'll say something of it'll be a Boolean combination of statements of the form I'm equal to AI or I'm not equal to AI. There's nothing else my language can say. And so if I'm equal to, I mean, if the formula rho, the quantifier free formula rho holds for b equal to one of the AI, this just says, well, then because the same equalities hold in A1 up to AN and AI, right? The same equalities hold in the set A as a subset of M and N. So then N says rho holds on the same tuple because, right, I mean, essentially rho can only say I'm equal or not equal to A1 up to AN. End of. So otherwise, as N is a model of the theory of infinite sets, I can find someone in N who's not equal to all of the AIs. So there is C in N, but not equal to A1 up to AN, universe of N. But then again, right, I mean, now let me write this. One's quantifier free formula in my language L are Boolean combinations of formulae of the form x is equal to y and not x is equal to y for varying variables, x and y. Okay, and now, because in this case, b is not equal to any of the AIs, this means the same equalities. So, b is not equal to AI, and C is not equal to AI for all AI. So the same equalities hold in the tuple A1 up to AN and B, and A1 up to AN and C. But I mean, some of the AIs might be, I mean, maybe A3 is equal to A5, whatever, but B is different to all of the previous ones, and C is different to all of the previous ones. So, and so Now if I plug this into my Boolean combination of equalities and non-equalities, the same equalities hold, so n holds on A bar C n.
If we're allowed to have, so we don't, our language doesn't have constant symbols, so we're allowed to have A be the empty structure. So why are we bothering with even picking A, like, couldn't we just appeal to like the fact that it's vacuously true if A is the empty?
Yeah, okay, I need to show it for all structures and for all common substructures. I've just not written down the quantifier elimination.
Oh, for all substructures, not a specific one. Okay, that makes sense.
Okay, so now I want to show the theory of algebraically closed fields, which you remember is the theory of fields together with every non-constant polynomial has a root, has QE in L ring, and I want to show it with a similar pattern. This is why I did the this first. But I need one more ingredient. It's an ingredient which already occurred in Sylvie's talk to some extent, if I'm not mistaken, namely elementary superstructures and elementary embeddings. Because, yeah, I'll tell you when I get to the point in the proof where I might what will happen in the proof of this theorem is there's one point where I might have to increase M or N, I guess N. So, and I increase it by taking the elementary extension. So this is in Tent and Ziegler, chapter 2. I'm hopping back for this now. We're in chapter 3 otherwise. Let A and B be structures in the same language. And map H between the universes is called elementary. Well, okay, so if it preserves the validity of arbitrary formulae, so if for all L formulae phi of x1 up to xn, and a1 up to an in A, I have phi holds on A bar in A if and only if phi holds on A bar in B. And in fact, one implication would be enough. Yeah?
Phi of, or B models phi of A or phi of H of A?
Aha, yes, phi of H of A. Thank you. And as elementary maps, in particular, preserve the truth of quantifier-free formula, right? They have to preserve the truth of all formula, in particular quantifier-free formula. They are necessarily embeddings in the sense that I've defined before. So any elementary map is an embedding, so it's injective and the relation symbol holds for someone in A if and only if it holds for its image in B. And we call H an elementary embedding. And sometimes, right, if H is the if H is an inclusion between structures, then maybe I just call the pair A and B an elementary extension. So write H from A to B with these. This is not a less or equal to, but it's like a curly less or equal to. or A lesser, so it's an elementary substructure of B if H is clear from context, or it's just, or in other words, it's just an inclusion. Okay, so example. Back to my theory of infinite sets. If A and B are models of the theory of infinite sets, and A is a substructure of B, which just means A is a subset of B, but then I just said elementary embeddings in particular preserve the truth of, any embedding, I should have said it the other way around. Any embedding also preserves the truth of quantifier-free formula. And so, if you have quantifier elimination, any embedding is necessarily elementary. By Q. Okay, so the example which occurred in Sylvie's talks, if A is an L structure, and I take any alpha power, you remember this was an alpha product where I take all the things to be equal to the same structure A, any alpha power, then the diagonal embedding, so the diagonal embedding maps an element little a onto the sequence which just consists of a's, modulo the equivalence relation on the alpha power, is elementary. And you check this by Washer's theorem. It follows immediately from Washer's theorem. And note, normally we're interested in alpha powers which are non-principal, so if U is non-principal, then this alpha product is in fact a proper elementary extension of A. It contains new elements. It just has a larger cardinality. Or maybe not necessarily. It definitely contains new elements. If it's principal, then it's just, then the alpha product is just the thing itself. Okay. So, of course, if A is a model of a theory T, and I take an elementary extension, then it's still a model of a theory T. Right? Because elementary extension even preserve validity of formula with things plugged in. But, being a model of the same theory just means the validity of sentences is preserved, which is less. So I'll apply this in the, proof ACF SQE. Okay, so take two algebraically closed fields. And let R be a common substructure, and without loss of generality, I let my common substructure to be finitely generated. Why can I allow my common substructure to be finitely generated? But I said up there in the quantifier elimination criterion, I really should show it for all common substructures. But of course, if I show it for the common, if I show it for the common substructure which is generated by my fixed A1 and up to AN, then it suffices for this single instance. So it suffices to only look at finitely generated substructures. So a finitely generated substructure, this is, maybe you don't remember what for me the language of rings was, but this is actually the reason why I included minus in the language of rings. So the language of rings was 0 and 1, plus, minus, and times, and now this finitely generated substructure is a commutative ring, right? Because it must be closed under all of these operations, so it's a commutative ring. So this is a finitely generated subring. I mean, that's what substructures are here. Okay, what do I need to take? I need to take, assume, there is a y, trying to use the same notation as in there. So then there is a y, rho of x bar comma y is simply existential. Rho is quantifier free, and it's an L-ring formula. And say K1 says there is a y, rho of, which way around am I writing it? A bar, comma y. I.e. K modulus rho of A bar comma B for some B in K1. Okay, so now want to show, let's say holds in K2. Okay, so what do? I increase my substructure R. Consider for I either 1 or 2 the field Fi, which is the fraction field of my finitely generated ring R in both K1 and K2. So just mapping right here, R sits inside K1 and K2, and now I form the fraction field of R inside K1 and K2, and so the fraction fields are naturally isomorphic because it's just fractions, right? So F1, there exists an isomorphism of fields, say F from F1 to F2, fixing R pointwise. Okay, now I'm extending my isomorphism little f of fields to an isomorphism of the algebraic closures of F1 and K1 and F2 and K2. And any isomorphism between fields will extend to an isomorphism between the algebraic closures, and because K1 and K2 are both algebraically closed, they will contain algebraic closures of F1 and F2. Extend to isomorphism D from F1 alg to F2 alg. Okay, so now I have an isomorphism between my algebraically closed fields, and I can already ask myself what happens if B is actually in the algebraic closure of F1. So if B is in F1 alg, then because isomorphisms are formula preserving, then K2 will know that what's the formula called? Rho of A bar, comma, G of B holds. That's because isomorphism-like structure. Okay, so, well, the other case, otherwise, B is transcendental over F1, or F1 alt. And then F1 alt joint B is isomorphic to, well, the rational function field in one variable over F1, right? I mean, it's an arbitrary transcendental, that's all I wanted to say. Okay, so if I now can find an X in K2, which is also transcendental over F2 alt, then I can just, a C in K2, which is transcendental over F1 alt, then these two rational function fields are isomorphic because they're rational function fields over the same algebraically closed base field. Just mapping one transcendental to another. So this is the case if F2 alt is not equal to K2, take C in K2, well, necessarily transcendental over F without F2 alt, and then K2, and then F2 alt joint C is isomorphic to F1 alt joint C, so K2 will know that rho of A bar, comma, C holds. Okay, but here this is why maybe K2 is exactly the algebraic closure of F2. Like maybe K2 is the rational, yeah, is the algebraic closure of the rationals.
So if, I'm a little bit confused, if R is like embedded in both K1 and K2, do we just know that F1 and F2 are isomorphic, or are they literally the same as sets?
Well, I mean, I guess this depends on your view of what fields are. For me, they are canonically isomorphic over R.
Mm. Okay, sure.
I mean, maybe for you they are the same.
Okay.
Okay. So in this case now, I need to, instead of taking, I need to increase K2 to find someone who's transcendental over K2. And I can do this by taking an ultra power. So if F2 alt is equal to take K2, take a proper elementary extension K2 prime of K2, e.g. by taking a non-principal ultra power. Maybe there's a subtlety. Note that algebraically closed fields are infinite, because otherwise, taking a non-principal ultra power, I set this up, I didn't write this down up there, but if you take a non-principal ultra power of a finite structure, it would not be a proper elementary extension, it would stay the same. So, but luckily for us, algebraically closed fields are infinite, so. And now any C in K2 prime without the algebraic closure of F2. And then K2 prime says there is an X such that row of A bar, sorry, this was called Y, such that row of A bar Y holds. But now K2 prime is an elementary extension, and this is this tuple A bar lives in the small field K2, so the same holds in K2. Yeah. And so K2 satisfies my, simple extension formula with A bar plugged in. Okay, so for the theory of infinite sets, we use quantifier elimination to deduce completeness. I want to do the same here, so this will be the second proof that the theory of algebraically closed fields of a fixed characteristic, of course, is complete. ACFP for P either a prime or 0 is complete. So let's do it for P a prime, and you'll see immediately how it works for if P is prime. K is a model of ACFP, then FP alg is necessarily a substructure of K. Because, but then, by quantifier elimination, I have FP alg is an elementary substructure of K. So for any algebraically closed field of characteristic P, I know its elementary equivalent to FP alg, so it's complete. And for P equal to 0, you just use Q. The algebraic closure of Q. Okay, so the next thing I'm promising you is a million corollaries from quantifier elimination and algebraically closed fields. How many is a million? Let's say 4. Okay, so far my first corollary, right, was of I would say of more of a model-theoretic nature. Completeness of ACFP is not, and I promised some number-theoretic applications. So let's start with, I guess that's more an algebraic geometric application. We're over an algebraically closed field, so things will necessarily have somehow a geometric flavor. So I want to prove that K be any field, and any proper ideal I in the polynomial ring in n many variables has a common root in all algebraic closures. Okay. So let's try. So proper ideal, of course, just means I, right? But by this I mean this is a proper subset of Kx1 up to the n. So if it's a proper ideal, that it's contained in the maximal ideal. Somehow my ideals seem to have capital I's. So now let's look at K adjoint x1 up to xn modulo m. This is a field, let's call it L. L is a field, L contains K. And in this field L, there's a prototype common 0 for all elements in M, namely just the images of x1 up to xn. So let's say the cosets of x1 up to xn for m are common zero. Of m. Okay, so now I want to use quantifier elimination of algebraically closed fields to bring this common zero somehow down from L to any algebraic closure of K. So I need one more, I need that ideals in, that this is a Noetherian ring, that ideals in K1, x1 up to kxn are finitely generated. So if I is generated by f1 up to fm, say, consider phi, the sentence which says there are x1 up to xn, such that fi, which is a common zero of my finitely many generators. So now by construction, L, my field extension of K, which is K, which corresponds to dividing out by the maximal ideal M, satisfies the sentence phi. So any algebraic closure of L will satisfy phi. Right? Because if I have a common root in L, I'll definitely find still one in the algebraic closure where I just make them, where I just have more choice. So for any algebraic closure L alg of L. But then, given an algebraic closure K alg of K, this sits inside some algebraic closure of L. And now by quantifier elimination, right, this sits inside this, this is a subfield of some algebraic closure of L, and by quantifier elimination, the corresponding embedding is an elementary embedding, so everything which holds with parameters from the smallest thing, which holds up here, also holds in the small thing. But phi, right, these polynomials fi are polynomials over k, so this phi is a sentence which uses, didn't write this explicitly, but phi is a sentence in which all non-logical symbols which feature come from k. K alg, so. Okay, so I want to do some more corollaries, but I need one more definition, which already featured in Bjorn's talk earlier today. So let A be an L structure. I'll be very explicit because there's this confusion about definability with parameters and without. So we call the subset B of A to the n A definable. So now I'm allowing parameters from A. If B is equal to all the tuples A bar from A to the n, well, maybe I should have said if there exists A1 up to M. Sorry, I didn't write this down well. Let me regroup. I deviated from my notes. That's always a bad idea. So, if there is an L formula phi in two lots of variables, x and y, both of a potentially different length, and tuple a bar in A, such that B is exactly the set which is cut out by those B bar in A to the n, such that phi of B bar comma A bar holds. And so it's cut out by a formula where you're allowed to plug in things from A. We'll do examples in a moment and then it will be very clear to you. In particular, right, my formula phi could be saying I'm equal to some element, whatever, pi, if I'm in the rings. Now I want to look at A definable sets in a structure A, or more precisely, K definable sets in the field K, and for now I'm considering K in the language of rings. No one ever tells me to raise the board. This must mean that no one in the back is listening. I'm trying to read what I write on the board. Not sure whether I should be offended by this.
Or it means that you automatically keep the board high enough.
Ah, no, that can't be true. My inclination is always to keep the boards too low because then I can reach them. So.
Usually know how to stand up.
In any field K, any constructible set is K, let's say K L ring definable. So a constructible set is a Boolean combination of zero sets of multivariable polynomials. And now, what quantifier elimination says is, so any constructible set, right, is a Boolean combination of things of the form saying, whatever, some polynomial equation in many variables is equal to 0 and not equal to 0 and, or not equal, So, and all of these, any constructible set is given by a quantifier-free formula with things from K plugged in. So in quantifier elimination in ACF says if K is a model of ACF, then all K L ring definable sets are constructible. I just can't do anything else. So I guess this is my next corollary. And in particular, if I look at a definable subset of the line of K to the 1, this now must be a polynomial equation, a Boolean combination of polynomial equations in one variable. So this is necessarily either finite or cofinite. Then be finite or cofinite. And this condition is called the theory of algebraically closed fields. Is maybe I should have written K definable. Is what's called strongly minimal. And somehow the moral is that if you look at strongly minimal theories in model theory, they behave with all the intuitions you gain from algebraically closed fields. There's a notion of dimension, strong minimality somehow the model theoretic analog of being an algebraically closed field, while not necessarily being a field. One last corollary. I think I promised you more corollaries than I'm actually delivering. So
You raised the board.
So another corollary, which is Chevalier's, or which is also known as Chevalier's theorem, is in an algebraically closed field, the projection of a constructible set is constructible. Right, because maybe I finished the word correctly. Right, because in an the projection of a constructible set is somehow you put a couple of existential quantifiers in front, but then a quantifier elimination tells you it's necessarily again equivalent to a quantifier-free formula, so it's again something of constructible form. Okay, so this was quantifier elimination in algebraically closed fields, and as you can see somehow, because all my fields here were algebraically closed, the bridges to mathematics beyond model theory were more of an algebraic geometric nature. So let's try real closed fields and periodically closed fields so that we can also get to other domains. Now, RCF and periodics. So I'll state the quantifier elimination result in RCF, but I will not prove it. Essentially it's proven, no, I've already erased the proof for algebraically closed fields. Essentially, right, you prove it again by the same criterion, you just need a bit more real algebra than what we know so far, Then I have time to cover. So I want to show the theory of real closed fields. You remember maybe? So it's a theory of ordered fields such that every positive element is a square and such that every odd degree polynomial has a root. That's the theory of real closed fields. So the theory of real closed fields has quantifier elimination in the language of ordered rings. So this was the language of rings together with a symbol for inequality. Maybe less or equal to. I guess that's what I did, it doesn't matter. And is hence complete. So the completeness follows in a similar way to how we just deduce completeness of algebraically closed fields of a fixed characteristic. Namely, there's a model which sits inside which sits inside all models, and by quantifier elimination, it's an elementary substructure. And this model here is the algebraic paths of the reals, so the real numbers which are algebraic over the rationals. So these are an elementary substructure for any real closed field K. So completeness follows from P.
But you could also take Q, no?
Well, I could, but I've not talked about, I've not talked about the criterion that having a prime structure plus model completeness gives you completeness. Though it's true. So, what's the analog of the constructible sets in the real world? So, it's semi-algebraic sets. So, in any, so these are polynomials polynomial inequalities, and multivariable polynomials being greater or equal to 0 or being equal to 0 and Boolean combinations thereof. And in any ordered field, any semi-algebraic set is K-definable, and like in algebraically closed fields, if K is a really closed field, then the K definable sets are exactly the semi-algebraic ones. So this is by quantifier elimination. In particular, we get an analog of this because semi-algebraic subsets of the line are finite unions of intervals and points. So if B is a subset of the line, and K is a really closed field, then B is a, probably said something wrong right now, right? I want to say a finite Boolean combination of intervals and points.
The union is
Yeah, that's also a union of, finite union of intervals and points, it's the same thing. Okay, and this property is called RCF. It's O-minimal. So for real closed fields, maybe this is not so surprising. If you've heard the uses of O-minimality before, the real power is that also certain expansions of the reals are O-minimal. For example, the reals expanded by an exponential function is still O-minimal, or the reals expanded by an exponential function and bounded analytic functions is still O-minimal. And then O-minimality, akin to strong minimality, gives you a very strong structure theory, which allows you to understand definable sets also in higher dimension, not only in one dimension. Okay, so let's do one corollary here, which is called Hilbert 17's problem. Take a real closed field. I guess for Hilbert 17, just take the reals. Then the claim is a polynomial f in n variables is a sum of squares. Sum of squares, say g1 up to gm in the rational function field k1 up to xkn, if and only if it's positive semi-definite. If and only if f of a1 up to an is greater or equal to 0 for all a1 up to an in k. Right, so this should say f is a sum of squares if and only if f is positive semi-definite. We wipe the board, you think about the proof. As so often, I sweep a bit of real algebra under the rug. What's the real algebra I'm sweeping under the rug? Well, I'm looking at the field. Okay, so if I have an ordered field, any element which is a sum of squares is positive. That squares aren't necessarily positive in ordered fields. And so sums of squares are positive with respect to any field ordering. And in a real closed field, you remember the converse also holds, right? This was part of the definition of being real closed. Conversely, if you have a field of characteristic away from 2 and an element which is not a sum of squares, then there's an ordering which makes this element be negative. It's not hard to check, but I don't want to do it. So I try to convince you to believe me. Assume f is not the sum of squares, then there exists an ordering on the rational function field k x1 up to xn such that f is strictly negative with respect to that ordering. Note that real closed fields possess a unique ordering. So this ordering less or equal to on this function field necessarily extends the ordering on K. So note this extends the given ordering on K, and so I'm saying this because I want to say I don't need to write 2 different symbols for my ordering. And it's,
What's an example of an ordering on such a field?
Maybe you want to put, you could put all of x1 up to xn as positive, and then their additive inverses are negative, and then it turns out this will give you an ordering on k up x1 up to xn. Okay, maybe you want to say where they lie, say they're all infinitesimally small. They lie, the x1 is less than x2 is less than xn, and all the xi lie between 0 and the small and all elements of k. That'll give you a well-defined ordering on this field. Maybe it's not the right one which makes f be negative, so maybe I should have switched the role. Depends on f, I might have had to switch the role of some of the xi's. Okay, so now every field has a real closure, so every ordered field has a real closure, so let this be the real closure of this ordered field. So every field has a unique real closure, up to isomorphism, like algebraic closures. But now in the real closure, I know there are x1 up to xn, namely capital X1 up to xn, such that f of x bar is negative, because f is negative. So the same, by quantifier elimination, the same must hold in K. So K is a substructure of L, and so it's an elementary substructure of L, and this is a statement about K, so with coefficients from K. So F is not positive semi-definite. Okay. I guess I have 3 minutes, but maybe, so the next thing I was going to say is about talking about quantifier elimination of the p-adic numbers, but I think that's the first thing I'll start with on Thursday. I have tomorrow off. So have a lovely evening.